Hello, linear algebra students. Oop, what happened here? Okay, here we're going to go over a few of the questions from your 6.3 homework. So the first question wants you to find the closest point to a vector y on the subspace that's spanned by v1 and v2. So v1 and v2, they're two vectors. They probably span a two-dimensional subspace. We're in R4, but I drew my picture in R3 just to make it a little simpler. We're assuming that y is probably not on that subspace, and so we're looking for the closest point to y on this subspace. So by Theorem 9, the closest point on W to y is the orthogonal projection of y onto W. And so basically what that means in the picture is from y, we go down to W in a way that will meet it orthogonally. And this vector is the one that's called y hat, which is the orthogonal projection of y onto W. It's in W, and this is called the distance between y and W because it's the fastest way to get there. It's the shortest, the closest point to y that's on W. If you took another point here, that distance would be longer. So we want to find the orthogonal projection. By Theorem 8, the way to find the orthogonal projection is to take the dot product of y with the first vector, divide that by the norm of the first vector, and then multiply it by that first vector. And then do the same thing with the second vector. So let's first compute y dotted with v1 and v1 dotted with v1. So y dot v1 is going to be 3 plus 2 minus 1 plus 26, because I did 3 times 1, negative 1 times negative 2, 1 times negative 1, and 13 times 2. And then v1 dotted with itself is going to be 1 squared, which is 1, plus 2 squared, which is 4, plus 1 squared again, plus 2 squared again. So when I simplify this all down, I get 30 over 3, which is 3. So now I'm going to put that in the slot here. 3 is that coefficient on v1. And I do the same thing to find v2. So I'll run through that one a little bit more quickly. You're dotting y with v2, so it's negative 12 minus 1 plus 0 plus 39 over 16 plus 1 plus 9. You can check my arithmetic, but this comes out to be 26 over 26, which is just 1. So that means that this part is 1. That part was 3. So to find the orthogonal projection, now I need to actually find this vector. Right now it's just written as a linear combination. So I'll have 3, negative 6, 3, 6, plus negative 4, 1, 0, 3. And then adding component-wise, I will get, let's see, negative 1, and then 5, and that one was negative 3. Negative 3 and 0. Actually, no, that looks like it should be 3. Okay. So that's all for number 12. This is the orthogonal projection, which we denote by y with a hat on it. This was negative 5. Okay, next up, we want to find the distance between y and w, which is the span of v1 and v2. So again, using Theorem 9, the distance is that shortest length between y and the subspace. So it's the length between y and the orthogonal projection. And length, or distance for us, is measured by the norm of the vector connecting those. So I'm looking for the norm of y minus y hat, the orthogonal projection. So first let's compute y minus y hat. So that's going to be 3 minus negative 1, negative 1 minus negative 5, 1 minus -3, and 13 minus 9. So we get 4, 4, 4, 4. And then the norm of that is going to be this dotted with itself. So I get 16 plus 16 plus 16 plus 16. That gives us the norm squared. And then we take the square root and we get 8. So this length is going to be 8. So that's numbers 12 and 16. And again, the key here is just that the closest point to y on a subspace is obtained by taking the orthogonal projection to that subspace. And then this length is the distance, the length of this connecting vector. And that's how we represent the connecting vector. All right, so let's move on to 18. On number 18, it's basically, the whole purpose is trying to get us to see a case of theorem 10. Theorem 10 says that the projection of y onto w is u times u transpose times y, where u equals the matrix with a spanning set for w. So if I make a matrix of all of the vectors that span w, and then I take u with u transpose, that's the same as calculating the orthogonal projection of y onto w. So the first step is just getting us set up to look at u transpose u and u transpose. So if u is a column vector, then u transpose is just that column vector flipped on its side. So it's a row matrix. So if I want to calculate u transpose u, I first do u transpose times u and so here it's basically just, you'll notice that this is sort of the dot product of u1 with itself. That's how we define the dot product of a column vector. This isn't always going to be a dot product because sometimes u is going to be like a 2x2 matrix. But since u is just a vector this time, it turns out to be the dot product. So 1 over square root 10 times 1 over square root 10 is 1 over 10 plus negative 3 over square root 10 times negative 3 over square root 10 is going to be 9 over 10. So we get 1. So this actually shows us that u is a unit vector, has magnitude 1. Next, we do u times u transpose. So I take my column, and then I'm multiplying by a row this time. So this time I'm actually going to get a 2x2 matrix because I'm going to do this times this, which is 1/10. This times this ends up here, so that's going to be negative 3 over 10. And then this times this is negative 3 over 10 again, and this times this is 9 over 10. So that's my u times u transpose. So these are my two solutions to part A. Now looking at part B, it's asking me to compute the orthogonal projection of y onto w. And since w only has one vector, we saw from theorem 8, this is the formula. I only have one term because w is only spanned by one vector. So I do y dot u1, and I'm going to run through this quickly because the dot product, you guys should be pretty familiar with computing that by now. So y dot u1 is going to be 7 over square root 10 minus 27 over square root 10. u1 dot u1 we actually just calculated. That's 1. So this turns out to be fairly nice for us. So we get 20 over square root 10 times the vector u1. So this is going to give us what? 20 over 10 and negative 60 over 10. which is the vector, simplifies to the vector let's see, 2, -6. Okay, now when I compute U transpose, oh shoot, this was -20. So this would be -2, +6. Okay, so now I want to do U transpose times Y. And by the theorem 10, we should get the same thing. So U transpose is here. When I multiply that by Y, I'm going to get 7/10 minus 27/10. It's my first component because I do that times that plus that times that. Now for my second component, I get -21/10 plus 81/10. And what do we get? We get -20/10 and then 60/10 again. So we do get the same thing. So those are the only three. So we checked theorem 10 for this particular case. Those are the only three I want to do in this video. Tune in to the next video for more.